B part 6, exterior algebra. Now, lecture 15B, following the previous lecture 15A, covariant derivative of two-form d omega. For this case, for lecture 15A, step 2, take partial derivative. I just copy from there and I'm right over here. You see, that we derived in relation the lecture 15A. Now, step 3, using Leibniz rule and Christoffel symbols. Since covariant derivative is a linear operator, so we can expand. You see, the covariant derivative of this is scalar, okay? Because I, and in this case, I and J, they are dummy. Likewise, K. You see, this is a scalar. So I can expand here and write down the three terms. This term over here, this and this term over here. So you see, I expand using Leibniz rule. So now recall that this covariant derivative, attention, VI is contravariant component which belongs to the vector space. You see, that's important here. So this I write down. You see, this is now I obtain partial of KVI. I just transpose the gamma to the right hand side with the minus sign over here. Likewise, similarly, the covariant derivative of the component Wj is as partial derivative of Wj. Now gamma k beta j v w beta. Now from here I can write the partial derivative with respect to xk or wj. I just this minus sign over here. So I can insert, okay, 2 and 3 into 1. Attention, see this mark here, the green mark here and the green mark there, and the blue one and the blue one. I just insert this expression on the relation 1. Then I match, you see, as exactly what I did in lecture 14. If you understood how to obtain lecture 14, okay, on this is exactly the same. So I match in terms and cancel, then you obtain this covariant derivative of the two form, okay, of d omega ij. I'm working here with components, you see, so this expression here. But you could, you see, develop this term over here, okay? Just you note that if omega is a one form, d omega is a two form. So I can expand, you see, d here as a two terms over here. You see, I have this partial I y, in this case, omega j, dxi dxj, as we did in previous lectures. So that's quite easy to see it. Since dxi wedge dxj is minus dxj dxi, the skew symmetric part survives. For you to see what I want to do with this term over here, I just use it for the particular case for I, j is equal 1, 2. So I expand d omega partial 1, that's first I'll do for I, the dummy index I, 1, 1, this is 2 and 2. Now I will expand for j. You see? So I expand for j. This term here leads to, this case, to two terms, and this term leads to also to two terms. That's why I have four terms over here, okay? Then I expand using j as a dummy index. You see, just quite easy to see it. Now, this one is 0 since the wedged, okay, dxi, dxj, they are skew symmetric. So this is 0, and also the last one is 0. So this leads to this relation here, partial 1 y omega 2 dx1 dx2 plus partial respect to x2 omega 1 dx2 dx1. Attention, you see the property of the skew symmetric. I can write dx2 wedge dx1 as minus dx1 wedge dx2. I can group this term. This leads to that term over there. Now I can extend this for I and j. So partial respect to xk of this covariant, this case, the d omega ij, you see, this is identical to partial I omega j minus partial j xj omega I. I can, if you want, to substitute this over here right there. So, no problem. But that's it. That's what I want to derive the covariant derivative of the omega ij. The omega ij belongs to the cotangent space, you see. It's important just for you always to remember that. You see, the omega ij is a components of a two form which belongs to the dual space. That's important. That's it.